Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitoris. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
All right, everybody. So it's time to get started. I'm Samantha Mabey. I'm Product Marketing Director of Cryptographic Security Solutions at Entrust, and I'm going to be your host for this morning. I'd like to welcome our first presenter. We're going to be hearing about advancing cryptographic transparency, CBOM standardization, and CycloneDX. We've got Basil Hess here. He's a senior research engineer at IBM Research Europe in Zurich. His focus is on the implementation side of cryptography, quantum safe cryptography, and quantum safe migration. Please welcome him to the stage.
Yeah, thank you very much. So my talk is about the work that we have done in standardizing Cryptography Bill of Materials, or CBOM, in CycloneDX. So I've organized the talk like that, or just start with a short definition of what is CBOM. We define it as an object model to describe cryptographic assets and their dependencies. We'll first talk a little bit about why we need CBOM, and then tackle a few of the core challenges in creating CBOMs that are actionable, so that can be used actually for the migration to, for example, post-quantum cryptography. Then we have a look at the CycloneDX project, which is a specification for all different kinds of use cases for bills of materials. And then we go through kind of a playbook covering cryptography, software, operations, hardware, services, and manufacturing. And then finally look at some of the tooling that is available, especially in the open source ecosystem. And then have a look at what's next, what's upcoming after this. So why CBOM? First, cryptography is really everywhere, right? You find it in source code, you find it in configurations that actually tell which crypto will be used at runtime. You have certificates in PKIs, you have services using cryptography, and hardware all related to cryptography. Now, there are more and more regulations and recommendations, for example, by states that require comprehensive inventories of cryptographic assets. One example is OMB M2302 in the US, and another one is the EU roadmap for the transition to post-quantum cryptography that specifically asks for a standardized format for the cryptographic inventory, for example, CBOM. Then why is this needed now? We are in the process of the migration to post-quantum cryptography, and usually inventories and CBOMs precede, or kind of is the starting point for doing that. And if we see timelines like CNSA 2.0, the migration needs to be completed by about 2033. And then finally, if you look at the ecosystem, there are different vendors, right, where cryptography that provide products with cryptography. So we need kind of a format that is interchangeable between different vendors and open source as well. So, but let's have a look at some of the challenges in creating CBOMs or an inventory. So let's say do a very first attempt to create an inventory. You can do something like that, right? So you do a grep for something that is not quantum safe, like Prime 256 version 1. And we want to see if this occurs in OpenSSL, right? So is OpenSSL quantum safe? If we do that, we find in one of the latest versions in OpenSSL 164 occurrences. Now the question is, okay, is OpenSSL quantum safe? Well, maybe, maybe not, right? Elliptic curve, at least, is not quantum safe. But we have to dig deeper. First, We have not found all the occurrences of this specific elliptic curve, because this one is also called P256. It's also called SecP256R1. There are occurrences of those names as well in OpenSSL. Then the next question is about dependencies. I mean, OpenSSL is a crypto library that provides all kinds of algorithms, but the questions probably is more like what is actually used, right, at runtime. Then another question is about post-quantum and especially hybrid, right? I mean, if this elliptic curve is used alone, it's not quantum safe. If it's used as part of a hybrid construction, it's probably perfectly fine. So we need a way to model that. So the next thing is what I call here configuration-driven crypto, or another term could be some definition of crypto agility, right? Where you don't specifically hard code what cryptography is used, but it's actually a decision that is made at runtime by some kind of configurations. CBOM is also about more than algorithms. It's also about protocols, which are used in practice, certificates, and other key material that is very important. And it goes beyond software, right? We need to think about hardware, services, operations as well. So what can we do here? And here I want to introduce CycloneDX. So what is CycloneDX? So CycloneDX is a so-called full stack Bill of Materials standard. It is an international standard, ECMA 424. And one of the very nice features is that there is one specifications for all kinds of different use cases, what you see here in the center. So it was originally designed for software, but was extended later to also cover services, AI, so AI models and data sets can be used, cryptography, which was the extension that we did, source code, hardware, and configuration. And one central aspect is what is called here BOM link, which is used to link together different components. So we have one specification, but we can use cryptography together with all the different other components and describe them. Then there are other features around compliance, about license and IP management, and about vulnerability management as well. So why am I talking about CycloneDX, right? If you look at this timeline, so this is at IBM Research in 2022, we kind of thought about how do we want to create cryptographic inventories, right? So we thought, okay, the first thing we need is to have some kind of specification how they should be reported, right? And then rather than creating something from scratch, we had a look around at the Bill of Materials standards, and we found that CycloneDX is actually a very good fit because it already covers software operations and more use cases. So we used that as a basis and extended CycloneDX with crypto-specific features. So we published that open source, and we were very happy that very soon the CycloneDX team came to us and said, hey, that's something that we would like to have in our core specification. So there was a crypto working group formed, and throughout 23 and 24, we worked on integrating that into the core specification of CycloneDX, which was then, the result was CycloneDX 1.6 last year. Soon later, CycloneDX was adopted by ECMA to become an international standard. So also the cryptography part is part of this standard. But we didn't stop the work there, but had some new features in mind that we wanted to cover and worked throughout 24 and 25. And then just exactly 1 week ago, I believe, 1.7 was released with some enhanced features that I will cover in this talk as well. But let's next dive in a little bit more about in CycloneDX and CBOM and look how it looks in a nutshell. So you see here, CycloneDX consists of different components. There is metadata, there are components, services, dependencies, and vulnerabilities. And I want to highlight the places where we add cryptography-specific features. The first thing is what you see in the middle. So we added a new so-called component type, which is called cryptographic asset, which can be either an algorithm, a protocol like TLS, certificates, or all other what we call related crypto material, which can be like keys and tokens and so on. So this is one central piece. And then another one is what I call here occurrence. So there is the feature of providing evidence attached to bills of materials, basically, which tells you how you identified certain components. So let's think about we scan software, right? So we can provide evidence where we found it, provide additional context, and can even also provide things like confidence levels if there was a probabilistic method that was used to generate the bill of materials. Then the last and quite central addition was directed dependencies. So CycloneDX already had the concept of dependency, but it was undirected. But we wanted to make the distinction between basically if cryptography is provided, for example, by a crypto library, or if it is used by a component. And that's what we added here on the dependencies. If we dig in a little bit, even a bit more into the specification, what you see here is the object model of CycloneDX. And in this case, a component, right, consists of crypto properties, which is either an algorithm, certificate, or protocols, and they come with a set of properties that can be described. For example, algorithms can be described, you can specify the primitive, like in post-quantum world, it will be like a chem or a signature scheme, define the algorithm family, but also specifics like where it runs, and if it's certified, for example, with a FIPS certification. Then with protocols, I mean, we started with the most popular, let's say, protocols like TLS, SSH, IPsec. And these protocols, they can be linked to other algorithms, right? So the cipher suites that are used, and also linked to related cryptographic assets, for example, keys. Then with certificate properties, what you see here, the properties in bold were additions for 1.7, because we had the request to kind of cover the most important certificate extensions, for example, NEX 509. So they can be represented here. One can also specify custom extensions. So there was quite some work on that for 1.7. Well, let's now come back. So that was kind of a quick overview of how CycloneDX looks like under the hood. But let's come back to the challenges that I talked about before. Remember, one of the challenge is to describe dependencies. And an example here is, for example, what you see here, right? If you do an inventory, you will probably find a lot of occurrences of SHA-1, right? And everyone knows SHA-1 is broken, right? Should not be used. But there is some context to it, right? I mean, many self-signed, root certificates, they are self-signed, right? And they often use SHA-1, which doesn't matter at all. Or if it occurs as part of a construction like HMAC, so the security properties are different. And now with the dependency here, we can actually provide this context so that SHA-1 is used as part of a construction like HMAC. Then another feature is in the context of hybrids. What we have, probably the most used PQC today in practice, is this X25519 MLChem 768, which is a combiner that combines a classical elliptic curve algorithm with MLChem. Now, if we do an inventory and just find the elliptic curve, right, we could mean that we are not quantum safe. But if we see that this is actually dependency for this hybrid combiner, so we added this primitive called combiner, we can see, it's actually we are using a hybrid, which is probably totally fine. This can be extended as well, right? Because cryptography is never used alone, right? It is provided by a crypto library like OpenSSL, which is then again used by an application like Nginx. And OpenSSL also provides this as part of TLS 1.3. So it's really kind of a powerful tool, these dependencies, that gives a lot of context to the individual cryptographic assets that are alone maybe not meaningful enough. Now, if we come to another challenge that I described before, is you could call it crypto agility, right, or configuration-driven cryptography, where you actually decide at runtime, right, or at deployment time, which cryptography will be used. So you will have kind of a configuration like OpenSSL, for example. You have the OpenSSL config file where you define which groups are used for TLS. Now in CycloneDX, we have this concept of an operations bill of material, which is exactly to describe configurations. Now connected with cryptography, we can have here this hybrid construction, right? And we can make a link and a dependency on a configuration. Configuration here is of type data and subtype configuration and lists where this configuration exists. And you can also give the content of the configuration. So this is, I think, a very powerful tool for these kind of use cases. Another use case is if you attended Navani's talk yesterday about a framework for crypto agility. If there is such a framework, it will be very easy to generate OWASPs connected with crypto information with such a service. Now, next, another thing, I mean, cryptography is not only implemented in software, but if you have, let's say, want to have high assurance, right, or in PKI use cases, you're probably using a HSM. Now, there is this feature of so-called xBOM in CycloneDX, where you can describe hardware. Like if you have an HSM like that, you can describe its hardware features, like it probably has a crypto coprocessor, some secure memory, some tamper detection circuit, some hardware RNG, so you can describe that. But now with the crypto extensions, you can also link that to the actual crypto assets that are provided by the HSM, for example, MLDSA or an AES key wrap. Another example is what is in CycloneDX. It's called a SaaS BOM, which is a concept to describe services or cloud services, right? I mean, that's often, right, so you don't install the software locally, but you use it over the cloud. Now, a SaaS BOM allows to describe services, so you can describe the endpoints. Say if data is authenticated, you can define trust boundaries, trust zones, and you can also classify the data in these services. Now, this is provided by SaaS BOM, but you can connect this to crypto-specific information like the cryptographic protocol that is used by a microservice, for example. You can say this uses TLS 1.3 with a specific set of algorithms. Another use case is what is called manufacturing bill of material, which is a feature of CycloneDX. And so this is about how a certain component has been built, right? In terms of cryptography, this is, for example, how a crypto module has been built, right? And you can specify the tasks, inputs, outputs, triggers, steps, and the runtime how this component was formed, right? One of the use cases here is to document, for example, the certification workflows that were done, or also the testing procedures for a crypto module. Now, next, I want to talk about a few new features that we introduced for the latest version of CycloneDX that was released last week, connected to cryptography. One feature that was requested by some participants from the working group is improving certificate lifecycle management. Already in the first release, we had the feature to define key management states for key material. So we followed the NIST SP 857 guidelines. So keys can be put in those states. Now with 1.7, we also added this feature for certificates. So you can say a certificate is in pre-activation, activation, suspended, deactivated, revoked, or destroyed. And then here on the right-hand side, that's how an example entry looks like. So you can describe the certificate, say this is revoked, this was the creation date, activation date, and revocation date. And then next, another, maybe one of the really core features of 1.7 was to tackle this challenge of naming ambiguities. I mean, remember, like there are many, I mean, everyone knows like triple des, right? But it is also, sometimes it's called des, DE, or 3 des, right? So you need to come up with a common naming to actually, that you have a CBOM, that you have different CBOMs, but describing the same algorithms. And also with Diffie-Hellman, right? We have finite field Diffie-Hellman, elliptic curve Diffie-Hellman. We also need to specify the elliptic curve to know what's the security level in there. Or RSA, right? RSA comes in different incarnations. It's a signature scheme. It's a public encryption scheme. It's a chem. There are different modes, different digests, different salt and key lengths that are all parameters of how you use RSA. Or even like quantum safe standard like MLDSA, right? They are different. There is a pure version, there is a pre-hash version, they are not compatible with each other, there are different parameter sets, and you somehow want to capture all of that. So our kind of goal was to come up with a list of crypto definitions. And now the question is a bit, how do you approach that, right? Because there are that many crypto algorithms, the list is growing over time. I mean, the first thing was that we don't want to bake this into the core specification, but to be able to extend the list outside the specification. And this is possible. So this is a schema defined in parallel to the core specification, but it's still part of CycloneDX. Then the second thing was that we want to have a good coverage of algorithms. And our methodology was basically, we started with the, let's say, most popular applications of cryptography, which is perhaps TLS, right? So looking at all the TLS versions, their specifications, extracting the algorithms that are used there. And then we go to the specifications that define the algorithms, like RFCs or IEEE or NIST standards, and extract the naming and all the parameters from there. So in this situation, for example, that's for RSA signatures PKCS1, right? And then we also define naming patterns where you can specify the digest algorithm or the key lengths. So the goal is really to have, like describing algorithms, right? It comes with all these different parameters, but that we have a unified way to describe that. Another addition was a list of elliptic curves. Because even they are not quantum safe, but they are still, I mean, of course, they are widely used. So we derived a list of curves from the standards curves project, which is a great source of all kinds of different elliptic curves with their parameters and so on. And we added this list as well to CycloneDX. Now, these are some of the new features and some of the challenges, right, that are tackled with CycloneDX and CBOM. But now the next question is probably, okay, that's the specification, but how can we use that? So a great source is the CycloneDX Tool Center.